So this is quite a nice statement that was published a while ago from George Brooks. But let's just delve inside to the bits that are highlighted. And the first thing he writes is this: look, lactate was considered for a number of years to represent the product of oxygen-limited metabolism anaerobic glycolysis during exercise. Lactate was viewed as a dead-end metabolite that accumulated during exercise, giving rise to fatigue and the oxygen debt. However, in contrast, data have recently been obtained that have engendered the concept that the formation, exchange and utilization of lactic acid, lactate, represents an important means of distributing carbohydrate energy sources after a carbohydrate meal and during sustained physical exercise. In other words, what George Brooks is really asking us to do is to move away from actually convention, which is to view lactate as kind of this dead-end product, this waste product, and viewing it as to being the all cause of local muscular fatigue, and actually recognizing that what lactate is in itself just a different variant of carbohydrate. If you think back to systems physiology and we go through the process of glycolysis, we start with either glucose or glycogen, whichever way we start. The end product of that breakdown process is pyruvate and or lactate. So in other words, what lactate is just a different form of carbohydrate. And what we now really need to be thinking about is lactate is not a waste product. Actually, lactate is good. This notion of lactate being bad is not correct, and in fact it's a false prophecy. In fact, we have to produce lactate because what lactate represents, really, rather than being this process of glycolysis, it's produced as a response of glycolysis. But it is not just because of glycolysis per se. It actually represents the shift from more fatty acid orientated metabolism to more carbohydrate based metabolism. But it is in no way is it itself a waste product, and actually in no way is the lactate molecule a cause of fatigue. It's much more complex than that. And so what we've got to do is keep that in mind as we go through both this podcast and all subsequent work in terms of the field of exercise physiology. So here's a conventional blood lactate response to exercise plot. So you can see that the squares represent the lactate response and the diamonds represent the heart rate response to incremental exercise. And what we can start to observe is, at a very broad level, is what is going on in terms of systems physiology. And what you can see quite clearly is that at 15 kilometers an hour there is a sudden, inextricable rise in the blood lactate concentration. Prior to that point it's been fairly steady. It's almost a linear-like response. And so what we observe is that there is a big sea change in what must be going on at the muscle. Now, the question to ask yourself is, what is happening at the muscle to drive this process? Why suddenly do we break away from this linear-like response? Now, this is in essence the be-all and end-all of our understanding of, in many ways, lactate production. And what you have to remember is that what you're recording in a capillary sample, when we take that capillary sample either from the finger or the earlobe, is you're taking that blood sample, and that is reflecting or is used as a proxy indicator for what is going on at the muscle. And that's a fundamental point to be clear on. What you're recording is used as a proxy indicator of what's going on in the muscle. Now the key thing is, for it to have appeared in the bloodstream, that lactate has to have been produced, it has to have been released, it has to have been transported, and then you have to have collected it. So why are we getting that response? Well, quite clearly what we can see here in this incremental response is, if we go up to that point of 15 kilometers an hour, quite clearly oxygen is not really limiting. How do we know that oxygen is not limiting? Well, look at the heart rate response. Heart rate at 15 kilometers an hour is only at about 162 beats per minute, with a peak heart rate actually at the end of this test, and this may not have been VO2 max, but a peak at the end of the test of about 178. So we know that oxygen isn't absolutely limiting. It's limited. Okay, so supply is not absolutely wholeheartedly meeting demand, so VO2 is not absolutely matching QO2 at the muscle, but it is not absolutely limited. And that gives us a little bit of insight. What this is suggesting is that as we go through these processes of incremental exercise, or as we change exercise intensity, and the demand for energy for the muscle to lengthen and shorten increases, the VO2 may well be outstripped by the QO2. So there is a mismatch between what is being demanded of the muscle and what is being supplied from atmospheric air. Supply doesn't necessarily meet demand. So in order to compensate for that, there is now an increased reliance on anaerobic substrate metabolism. So the process of glycolysis becomes engaged. So we start to move from a less fatty acid orientated response to a more carbohydrate orientated response. Now, we have not shifted to wholly anaerobic metabolism, let's be absolutely clear. What this is suggesting is that there is an increased reliance on carbohydrate metabolism, some of which will be coming from the TCA cycle, some of which will be coming directly from the first 10 stages of glycolysis. Quite clearly, the use of the TCA cycle is an aerobically dependent process. So if VO2 is not matching the QO2, that in itself will not be able to necessarily supply all of the energy required for the muscle to lengthen and shorten. So some of the derived energy will come from glycolysis. And so, for example, if we look at 12 kilometers an hour, if you look 12 to 13, there's a rise. And you'll see in subsequent podcasts, this point is referred to as the lactate threshold, or LT1. And it really suggests to us this point where you get this first change in substrate metabolism. So we've moved from a pretty comfy zone where VO2 is absolutely matching QO2, where it's predominantly coming from fatty acid metabolism. Now we've got this increased reliance on carbohydrates, but not substantially, because again, look at the heart rates. The heart rates have only gone from about 135 to about 145, so it's not very high intensity exercise, but an additional contribution in terms of the supply of energy is now coming from the TCA cycle and carbohydrates. But some will also be coming from glycolysis. Remember, these processes do not work independently of each other. They are all working in conjunction. It's just the relative contribution that changes. But as the intensity starts to increase, we go from 12 to 13, now clearly the athlete has to run faster. So now we need to produce more force at the muscle to increase the running speed. So we're either going to recruit more muscle fibers, or we're going to produce more force per fiber. Either way, they're going to require more energy to do the work. So again, there'll be a ramping up of substrate metabolism through the TCA cycle. There'll be a ramping up also through glycolysis. So we increase the amount of energy being provided from the aerobic and anaerobic processes. And that keeps happening until you get to 15 kilometers an hour. At 15 kilometers an hour, this is where the sea change occurs. The predominance now shifts from getting the energy from predominantly aerobic sources to predominantly anaerobic sources. We have not switched to just anaerobic sources. We know that, again, because look at the heart rate. The heart rate is still rising, so that tells us that we're still getting a good supply of oxygen, VO2, to meet QO2 at the muscle. It is just that we have now gone to this point where the greater proportion of energy is being derived from anaerobic substrate metabolism compared to being derived from aerobic substrate. The net result is that if we are deriving more energy from substrate level glycolysis, that there will be an increase in hydrogen ion production. And this is the fundamental point. Hydrogen ions are produced as a result of substrate metabolism. We understand that there are hydrogen ions that are produced, and when they are produced under low intensity conditions, the hydrogen ions are shuttled down to the electron transport chain, and as a result of being moved down the electron transport chain, we end up producing As a result of being shuttled down the electron transport chain, we end up with producing ATP. However, as the rate of substrate level metabolism starts to increase, we will start to produce more hydrogen ions than we can get onto the carriers, the NADH, the nicotinamide adenosine dinucleotide hydrogenase, or the FADH, which are residing within the electron transport chain. So now we get excess hydrogen ions. Where do they go? Well, they can either go into the cell and actually attach themselves to troponin and therefore start to prevent actin and myosin bonding, or they will attach to pyruvate, which is the end product of glycolysis, and the net result is you now produce lactate. And that lactate is what you are measuring in your capillary sample. So, as exercise intensity increases, hydrogen ions will still be going down the electron transport chain, because we're not running out of carriers per se. What we are doing is we're producing more hydrogen ions than we've got carriers. So if we've got more hydrogen ions than we've got carriers, as the intensity goes up and the rate of metabolism increases, you'll have a backlog. Some of which will go into the muscle cell, but predominantly what tries to happen is that those hydrogen ions will attach to pyruvate to produce lactate. Hence your blood lactate concentration goes up. Clearly, at 15 kilometers an hour, there's been this shift from predominantly aerobic to anaerobic metabolism, which tells us that the majority of the hydrogen ions are now attaching to pyruvate to produce lactate. Some are going down the electron transport chain, some of the pyruvate is going through and is converted to acetyl coenzyme A and enters the TCA cycle. But as the intensity goes up even further, less of the energy that is being used for the generation of force and generation of ATP, less is coming from the aerobic sources and more is coming from those glycolytic sources. More hydrogen ions are being produced, more of a backlog because we've still only got limited carriers down the electron transport chain. The net result is that we have greater lactate production. And so that is what you're measuring when you take your capillary blood sample. You're measuring, in essence, that change in substrate metabolism at the muscle. It is not just about supply of oxygen and not meeting demand for oxygen. It's a much, much more complex process than that. But what we want to do now is start to understand in detail what this process is. We've talked about the glycolysis sitting behind it, but clearly that's going on in the cell. But you're measuring in the blood something that is extracellular. So how do we go from an intracellular environment to an extracellular environment, and in essence what you record in the bloodstream? So this is from a really nice paper in MedSci Sport and Exercise published by George Brooks quite a while ago now. But this really summarizes for us, and in many ways this is the most important schematic that you'll come across. It summarizes everything we've been referring to. So on the x-axis you can see work rate. On the primary y-axis, so that is on the left-hand side, you can see what is referred to as the rate of appearance and disappearance. It's got no units. On the secondary y-axis, you can see the blood lactate, so the blood lactate concentration in millimoles. So if you look at, first of all, at the blood lactate curve, and that is highlighted with the triangles and the dashed line, you can see a representation of what is conventionally shown in a textbook for the blood lactate response to incremental exercise, exactly as we referred to before. This notion that at low intensity exercise there is a fairly linear-like response in terms of the blood lactate concentration until we get to this point referred to as LT2, highlighted by the arrow, and at this point, LT2, which is lactate turn point, we suddenly get this curvy linear response, and you get this almost exponential increase in the blood lactate concentration. What this graph actually allows us to see, this schematic, allows us to see, is Y. And you've got these two additional lines referred to as RA and RD. RA refers to the rate of appearance, RD refers to the rate of disappearance. Now, here's the thing. When you produce lactate, remember that lactate and what its constituents are, we don't really want them in the cell for two reasons. One, lactate contains hydrogen ions, but two, here's the fundamental part. Remember what lactate is. Lactate is a different form of carbohydrate. So if it's a different form of carbohydrate, surely one would argue the most logical thing to happen is that substrate could be moved from a cell where it's being produced and taken up to a cell which is less active, for example, and converted back from lactate to glycogen to be used as an available substrate, released as glucose and transported through the circulation. And that is what happens. So what we start to understand is that as we go through the process of incremental exercise, we get a step change in fibre type recruitment. We go from slow twitch to type 2A to type 2 fibres. Not that we just turn off slow twitch, it's that the slow twitch struggle to meet the lengthening and shortening requirement. So we increase the recruitment of type 2A, and then we go to type 2 fibres, type 2B fibres. At low intensity exercise, we can see that the blood lactate concentration is low. What happens is that the lactate that is produced in the cell is released, and it is released from the intracellular environment into the extracellular environment. Under those conditions, the rate at which it appears is matched pretty much by the rate at which it disappears. So the rate of disappearance is the rate at which it is taken up by other cells. These are either cells that are less active or cells that are in themselves inactive. And we'll come to how that works later on in terms of how that process occurs. So quite clearly what you can see up to that point of turn point, can you see that there is pretty much a matching between appearance and disappearance, but quite clearly that the rate of appearance slightly deviates away from disappearance. Not massively, but enough to explain why the blood lactate concentration rises gradually. Because you are producing more, so the rate of appearance goes up, but the number of inactive fibres, the number of sites for where the lactate can be converted back to pyruvate and then technically back to glucose and glycogen, that number of sites will not change in terms of you're not going to get more sites, you're more likely to get less sites. So the net result is that the balance, you see the gap between the appearance and disappearance just slightly starts to become bigger. Now when you get to turn point, look what happens. At turn point, where the arrow on the blood lactate curve appears, remember what we suggested, that at that point, the predominant substrate is predominantly from anaerobic metabolism. Now, the rate of appearance suddenly exceeds quite extraordinarily the rate of disappearance. And now the gap between the two becomes far, far greater. You're producing more lactate that can actually be taken up in other cells. So in other words, appearance starts to exceed disappearance. And that starts to drift away further and further as we increase the exercise intensity. So at low intensities, appearance and disappearance are balanced. Hence the blood lactate concentration doesn't rise. As we start to increase exercise intensity and we produce more lactate, the appearance starts to become greater than the disappearance, the lactate concentration increases. So this really informs us about what it is you're recording when you take a capillary blood sample, that in essence what you're actually recording is the outcome of appearance versus disappearance. So when the lactate concentrations are low, one can speculate quite nicely that what you're recording is a good balance between appearance and disappearance. But as the concentration rises in the blood, that clearly indicates that the rate at which it's disappearing is not matching the rate at which it is appearing. So why does more appear? Well, it's probably fairly obvious, partly because you've got that glycolysis rate increasing because there's been an increased demand of the muscle to do work. But secondly, the other thing to bear in mind is that we have a natural buffer. And the natural buffer that we have, and this a buffer you should think about being a bit like a sponge, something that absorbs the lactate and prevents the lactate in itself from causing damage either to cells or the like, is bicarbonate. Now bicarbonate is an alkaline, lactate is by definition an acid. And what happens is that the bicarbonate acts as a natural buffer, but the bicarbonate is limited. So there is a point where we don't have enough bicarbonate available, So the net result is when that happens, the rate of appearance starts to increase, that the lactate starts to come out of the cell quicker than it can be disappeared, because now you haven't got enough bicarbonate to buffer it. And then that's coupled with the fact that you cannot increase the available sites for disappearance. In fact, more likely what's going to happen as exercise intensity increases, the number of available sites starts to decrease in terms of disappearance, because maybe you've engaged more muscle fibers. So that's a really important construct that we're seeing here, that lactate curve, the lactate response to exercise that you record when you take a capillary blood sample, is a representation of the balance between lactate rate of appearance and rate of disappearance for lactate. So it's a really important proxy indicator of what is going on at the cell.